Everyone. Thanks for joining us. This is Caroline Griffin, Riot's Director of Operations. Welcome to the Riot Lunch and Learn series, where we feature all of our wonderful partners. Today, we have James Thomason from Edgex with us today. Super excited. Edgex just joined our ecosystem. They spoke at our Edge Computing event back in January, and they are fantastic. And I know you guys are just going to love this presentation. Just a couple of quick reminders before we get started. This presentation is being recorded and will be posted to Riot's YouTube channel and the meetup page where you registered for the event, so you'll be able to find it afterwards. If you have any questions throughout the event, please do post those in the chat box, and I will make sure that James answers all of your questions after the presentation. Without further ado, I know that you guys are here to see James and not me, so I'll hand it over to James. Thanks for being here with us today.
Hi, everyone. Can everyone hear me okay? Okay, I see some nodding. That's excellent.
Yes.
And let me just share my screen. Can you guys see my slides okay?
Wonderful. Thanks, James.
Okay. Well, thanks so much. We have a lot of attendees. Thanks so much, everyone, for coming. Really excited to talk about myself. No, talk about Edgex and tell you what we're doing. I know I have about an hour and I have like 140 slides, so fasten your seatbelts. What I'm going to do is just tell you up front. I think a lot of this audience is pretty technical, so I'm going to try to gloss over some of the businessy stuff because I think you guys being an IoT audience, you all get it. And then get into kind of the weeds of how we work, and it'll get increasingly technical as we go along. So if you are a technical person, bear with me for a few minutes. And at the end, I'm going to try to do a demo. I don't think I have enough time for a live demo to leave time for questions. So I'm going to go through like an accelerated recorded demo on 5x speed and give you the narrative. So very briefly, if I can advance my own slide. Okay, sweet. Just none of us that have ever met before, I don't think, outside of the immediate folks we've met at Riot. So my name is James Thomason. I'm the CTO and co-founder of Edgex. We're a startup company headquartered in Raleigh. Although we are spread out all over the world, we have staff everywhere. I've been doing startup companies in Silicon Valley primarily for the last 20 years. I've done about 14 startups because I'm insane. I've returned about $1.1 billion to investors. I have a bunch of patents. And some of these logos you may recognize if you've been around a long time. Some of them you may not. But I started my career as a network and systems infrastructure engineer and architect, building out the first generation of the internet, what we call the Al Gore internet. And beyond into the dot-com era, through the dot-com bubble, the dot-com crash, the birth of mobile, the birth of cloud, and now into IoT and Edge. So that's just a bit about me. You can follow me on Twitter. I love it when people reach out and say hello. You can find me on LinkedIn. I'm very easy to find. You can find me at jamesthomason.com. Enough about me. We started Edgex actually. So I sold my last company to Dell, which became a product called Dell Active Systems Manager, if any of you are infrastructure hacks. And I told my wife at the time, like, I'm absolutely not going to do another infrastructure company. That's it. There's no more. I'm going to go do marketing. And so I did. And then I got together with my current partner, John Cowan, who's CEO of Edgex, and we started talking about the fourth internet and the trillion connected things that were coming. And I sort of realized I'd be walking away from the mother of all infrastructure trends. And the more we looked at the problem, the more we realized that this was going to be a huge moment. And so I think everyone on this call probably gets this intuitively, but the way the world works right now in the current incarnation of the internet is that out in the cityscape, we have all of this last mile connectivity, whether it's broadband or cell and 5G coming with picocells and femtocells, satellite from Elon Musk. And most of the backend for our mobile apps and our IoT apps runs in some centralized cloud somewhere, whether you're using any of the big three or something else. And this necessarily means that there's a bit of latency between the centralized cloud and the connected things and end users at the far edge of the network. And the simple truth of that is that cloud is not going to keep growth with edge data demand. So when John and I sat down and did the back of the napkin calculation, we realized there was something like 45 to 60 zettabytes of stranded data at the far edge of the network today. That was growing at a 25 to 35% CAGR. And so just 5 years in the future, you had an insurmountable amount of data This is a technical audience, but for the non-technical folks, I usually tell them a single zettabyte is like the city of Manhattan constructed out of 1 terabyte SSD drives. And that's about right still. And so 60 cities of Manhattan made of SSD drives growing to 180, 200 Manhattans of SSD drives is a whole lot of data. And 5G, or the growth in broadband, et cetera, is not going to overcome that shortfall in bandwidth. And then even if it did, you have the latency problem of, for the first time in history, computing is moving out of the realm of the abstract and into the real world. So it's no longer about necessarily mobile apps and browsers and that stuff, although we clearly want to accelerate that stuff and make augmented reality a first-class citizen, if you will, as it comes to fruition over the next few years. But it's also about doing stuff in the real world, driving cars, operating heavy machinery, factories, all the things that we're doing in the IoT space. Sensor data fusion, looking across multiple data sources to make decisions and conduct actions in the real world. So when we looked at that together, we realized that the cloud was going to have to change. We weren't going to backhaul things to a centralized cloud. The pendulum would swing from centralized back to distributed once again, as it has done many times throughout the history of computing. And we would need to deliver ultra low latency cloud services at a high bandwidth. It would need to work and sort of look and smell like the cloud, but it wouldn't exactly be the same underneath. And the idea was to put this anywhere and everywhere. And so our ambition at Edgex and what we're building is a new type of content delivery network that spans the planet. And so we literally mean that, as I'll show you. We want to bring edge computing anywhere and everywhere, 1,000 feet away from users and connected things, everywhere that it matters to do that. And if you think about today's world of CDN or the old edge, there are hundreds to low thousands of points of presence, depending on who you're talking to. And their diagram for CDN looks something like this, where end users are directed to some regional point of presence where there's a good set of network, aggregated network connectivity and so forth. And there's billions and billions of dollars invested in these kinds of CDNs and points of presence. What we want to do is build a network that gets much closer. And so you can think of this done at the city level, where there are hundreds of points of presence, like within a given city, as part of the city's actual infrastructure. And the timing is right to do this because smart cities and the idea that there's a reservoir of data inside of cities, which cities themselves can monetize and turn into new revenue streams, that might even dwarf today's existing property tax revenues and that sort of thing. The timing is really great for that. Plus, you have these other trends that are dovetailing, like 5G, serverless computing, and as we'll talk about, peer-to-peer cryptographic stuff that makes this all possible. And so what we are doing is we're about to announce, I don't know if the press release went out today or it's imminent. We're announcing our partnership with the Autonomy Institute and the companies that are inside of it. If you haven't heard of Autonomy, what they do is they make this enclosure you see here, which is called the Public Infrastructure Network Node. And by laying fiber throughout the city or taking advantage of existing fiber and anchoring these things to street corners, these sort of replace or augment the lighting and other things. But inside of these long silver pole looking devices are a whole bunch of sensors. There's ground level GPS, there's lighting, of course, for the surrounding area, backhaul with Starlink, 60 gigahertz, there's radar, LiDAR, other proximity sensors. There are cameras and even audio in some cases. There's CV2X connectivity and what would have been DSRC if we hadn't abandoned DSRC. And a whole bunch of wireless connectivity. And one of the things that's changed in the last few years is this idea that we can now use unlicensed spectrum to bring wireless and high speed, low latency wireless into areas like this. And so previously, I think in the United States, we're all aware that the telecoms have been hoarding their spectrum, and that was the way that they sort of defended their market space. But with CBRS and LTE-U, we can now go in and through neutral tower protocols, et cetera, we can now offer wireless and actually augment the existing sort of carrier networks to deliver higher availability, higher performance, et cetera. And so in these pins, we are putting edge computing infrastructure because, again, the problem is latency and bandwidth. The things that are in these pins need to work at ultra low latency. And the idea is that we can deliver those services to the things inside the pin, but also we can create a little mini cloud around the pin to serve the users and connected things in close proximity. And as you might imagine, the first idea for this was to sort of connect these things and backhaul them to some point of presence, like a regional, just like you see in the old CDN, like a regional point of presence or something. But that turns out to be too far away, and a lot of the things that they're planning to do out of these devices are not really suitable for scenarios where they can become disconnected from the brains, if you will. And so that really necessitates edge computing. And I think when most people think about edge computing currently, they think about something like this, where you're just going to take Kubernetes or some sort of the stuff that we built for the cloud and deploy that to an infrastructure that lives in the pins. But when you do that, a whole lot of other challenges emerge. And so you've got very constrained resources on these devices. You don't have a whole hyperscale data center of stuff. You have whatever you can fit inside of one of these pins. You need to orchestrate getting developer software like onto these things and to interact with the things that are inside the pin. And most of these IoT devices were not designed for multi-tenancy. So you have a multi-tenancy problem, you have a software delivery and orchestration problem, tons of security challenges with running untrusted code in an environment like this. And then you have the usual problems of data gravity and data integrity and resiliency. So the idea that, nefarious people could open these cabinets and pull out drives or compromise them in another way. And then your data that you're persisting, in a natural course, you have state that you need to keep somewhere. That data would be local in today's architecture to the pin. And so what you need is a way to get that data elsewhere. And so just in kind of a cartoon way, I talk about it like this, like the general notion that people have right now is that we're just going to straight up take the stuff that we built for cloud and extend it to the edge. And as kind of a joke, the way that I say that we deal with complexity in the cloud right now is that we orchestrate the crap out of it. And over the last 20 years, we got really, really good at orchestration. I mean, to the credit of the authors of Kubernetes and other things, HashiCorp, et cetera. And they're all amazing orchestrators compared to the ones that we used to have to build. And I feel like I spent the first half of my career building orchestrators in various ways to put code in production or to run production infrastructure or test infrastructure. It was a real burden. And so that's a lot better. And this sort of thought is that you're just going to turn around and then orchestrate the things at the edge using the same stuff. But I want you to really think about that, what that might mean a little bit, because in the scale of something like Edgex, or this idea that there's a ubiquitous utility grid of computers, if you will, that we can take advantage of. So the orchestrators themselves can do a lot of things in parallel. They have a lot of arms, but they aren't particularly smart like themselves. So you've got to take what's in your brain as a developer or as a system administrator or architect and sort of translate that into something the orchestrator can understand. So you think abstractly in general about how your application works and how the components need to work, and if those microservices have to talk to each other and messaging and the data layer and all that stuff. And then you sort of translate that into YAML. And in the case of today's orchestrators, it's like a whole lot of YAML, like a huge proliferation of it. And if you really think about doing that on the scale that we're talking about, where you have something like Kubernetes clusters running on each one of these things as sort of a microcluster. And there are great cases of that have happened already, like Chick-fil-A is doing that in its 5,000 retail locations, et cetera. So there are examples of that working, but in this change to what we call the fourth internet, it really is more dynamic than that type of infrastructure will support. And so for me, if you sort of follow the logical progression, you started with K8s, like full-blown Kubernetes, and then they get it down to K3s, which is a cut-down version. And our mindset is like K0s, like no orchestration, no containers, no virtual machines, none of that stuff that has tight infrastructure dependencies. And that's upsetting for some folks, and it's hard to get your head around because this world of the centralized hyperscale cloud is a very neat and orderly place. And I want to emphasize that, like, it's gears turning gears turning gears. I've often said that developers and sysadmins, they're like the clockmakers of this century. They love the little gears tools and frameworks that make things work and snap together neatly. And that is, after all, part of the Unix philosophy, right? We write programs that do one thing and do it really well, and those programs work together to achieve a bigger end. And there is, however, a lesser known element of the Unix philosophy that goes back to the original Thomson-Ritchie paper, and it's this idea of economy and elegance of design due to size constraints, or salvation through suffering. Small is beautiful, simple is better. And let's be honest, this world we've created today is a terribly complicated place. We've forgotten about economy of elegance, and we take size for granted. And we may have even sacrificed the last 5 or 6 years of Moore's law because we had the cloud. We could just add more of what we had, build another data center, add more servers, keep adding. Who really cares about efficiency in that state? I mean, we care about power efficiency and stuff, but is it really worth cramming more circuitry onto a chip? And so I like to think that we gave up a lot of that over the last decade with cloud. So the real world in the edge and IoT is going to be a very chaotic place. So rather than this neat picture, it looks more like this, where there are cases where obviously users are mobile and sensors tend to be fixed, but users interacting with sensors is something that happens, that needs to happen dynamically, whether that's the user in this case is something like an autonomous vehicle, or a user with their mobile phone or an app that's running on the phone. This idea that they're all moving around, and the data that they're generating and interacting with needs to be fast, and the execution of the backends needs to be very fast. And if you think about the cloud in a lot of ways, sometimes people argue with me about this, but I see the cloud as really a response to the growth of mobile. We all started carrying around these inferior computing devices compared to our laptops and desktops. They're awesome, but they're not particularly powerful. And borrowing capacity from the cloud was a way to deal with the data processing requirements of all that we need of these mobile devices. And so that's times like 100 in IoT. And if you think about this in the context of the squid we were talking about, presupposing how you're going to make the infrastructure ready to interact with these devices and things is a non-starter. Like, you don't know in advance how or where a user or a thing is going to show up in this sort of ubiquitous layer. I mean, it's very static right now, but it's not going to be, is kind of the point. And there are, the problem with data is that it's really hard to have a one-size-fit-all strategy, because some data is hot and has to be hot and has to respond in real time. Some data has to be warm, not too far away, and other data can be cold. And the sort of the best that we have right now, that's the general fit purpose, is this this notion of blobs, and shoving blobs into key value store, or whatever we want to put there. But it's not yesterday's structured databases, SQL, et cetera. And so that's kind of the direction that we've undertaken. And we think what liberates us from all of this chaos is the idea of serverless. And I've always hated serverless as like a descriptor, because clearly there's a server somewhere. But it's just the idea that the developer is free from the infrastructure, and the infrastructure is smart and knows where to put code and so forth. So triggers and actions. Okay, most things, especially in the IoT space, can be tied down to an originating event. Whoever is generating data, whoever is requesting data, these are triggers. And serverless really neatly can be used to fulfill that. And in order to make it really work, we have to change the way that virtualization works, and we have to change the way that data gets persistent and moves around, which I'm going to get into. But the big, I think it's wonderfully ironic that the ultimate cloud technology, serverless, which was really, Genesis inside of AWS is going to be kind of like the thing that puts cloud to rest or puts cloud in the background in a way. It's not to say the cloud's going away anytime soon or ever. It's just that what we think of as the cloud today will change, and these big centralized data centers will take more of a background role compared to all the growth that's going to be at the far edge of the network. So how do we make this work without the squid model? Well, I started thinking again. You saw my background, so I've been in this since the Al Gore internet, and a lot of my childhood years were spent routing packets for food. And the thing about that architecture, well, I mean, the fathers of the internet were pretty smart people, and we're still using their stuff 40 years later. And I think it's interesting, like at the big, the big three, the big tech companies, there's a lot of these gray-haired, grandfatherly folks running around because the younger generations don't yet know, in excruciating detail how all of this stuff works yet. So there's kind of a rebirth of, and you see, like, you go to Big G or Big M or any of these companies, you'll see the graybeards running around, and it's kind of always been the case in computing. But the creators of the internet lived in a very resource constrained world, and so the way that they dealt with that is they pushed off a lot of the state into creating smart protocols. And so the state machine could run in really constrained environments, and you were dealing with data on the fly, and that sort of worked. And so that got me thinking, well, what if we could do this same kind of model? I mean, routers on the internet, what they do is they speak a protocol, and they exchange information about the state of where addresses, IP addresses, are reachable. And IP addresses are basically a location, a physical location on the network somewhere, a logical location on the network. And that got me thinking, what if we could do the same thing for data? And it turns out, of course, that someone else had thought of that before me. And it's this notion of content addressing, which we'll come to. But if we could build this in a truly distributed way, like a peer-to-peer way, then we could make a protocol that was smart enough to bring code where it needed to be in response to a trigger, and in response to a protocol level request. And we could bring data also wherever it needed to be in this kind of network, like on a moment's notice. And if we went further than that and built in data integrity and replication strategies into this protocol, we wouldn't really have to worry about nodes on the network anymore. They could come, they could go, people could steal them, cars could run into them, and we really just wouldn't care. We would just, take our sweet time and build another one of these things or deploy another one when the time came. And that led us to the design of Edgex. So starting, into the technical weeds a bit, what Edgex is an operating system that runs on bare metal or machine, or actually our stack can actually deploy as containers, or you can put us on Linux or whatever. But our primary deployment artifact is a operating system based on FreeBSD, and that operating system has our magic bits inside. Primarily this peer-to-peer protocol, but other things as well. So it has, as we'll come to, all sorts of different protocol endpoints and magic. But the sense of that is that you can, as a developer, you can write serverless functions and then sort of push them into the network. And those functions will show up on the far edge of the network and run wherever they need to. But you can also do that with data on Edgex. So in this diagram, what's happening is we have three EdgeNet nodes. And these nodes are connected in proximity to some things like sensors, basically. And the cool thing about this is that you can configure your sensors just one time, at the factory, and then give them this content addressed endpoint. And our network will take care of routing them to the actual physical node that's nearby, done through layering of DNS and HTTP proxies and other protocol proxies. We just sort of make that happen. Trust me, it works. So we do the same thing for like mobile users. So mobile users can just request an application ID, and they'll get routed to the local node that's closest to them. And the network will take care of delivering the serverless function or delivering the data that they're looking for to that local node. And it will do that intelligently. And we're building in other things that make this, I'm just double checking my time here. Yeah, I have a little more time. that make this pretty intelligent. So in the case where a car is traveling down a street, we can bring the warm data forward into nodes that we know they're going to be traversing in a few moments time. And so in this way, we can keep an application accelerated, even dealing with things like vehicular motion or pedestrian motion, et cetera, drone motion as the case may be. So what happens is that a thing wakes up and wants to send data somewhere. It does that over a protocol like HTTP or MQTT, and a handler that a developer has written wakes up, if you will, on a node and processes the data, persists it, does whatever it does with it. And in this way, you can begin to build distributed applications where the concatenation of triggers and events in sequence and series lead to complex functionality over time. And any of you who've been working with Lambda, et cetera, this will be pretty intuitively familiar. The next, well, to peel back the onion a little bit further, what's inside of EdgeOS is a lot of things. One is a set of proxies, protocol. These are protocol endpoints like for HTTP, HTTPS, MQTT, other nasty IoT protocol proxies, basically, that run on every node. And one of our tricks or design criteria was to try to make every node utterly identical with no configuration, because because I hate configuration, for one thing, and configuration is part of what makes things complicated, because it's the resolution of configuration against a runtime environment is what causes all of our pain and problems when things don't deploy the way that we expect them to, when we change environments and that sort of thing. And what we want to try to do is make everything work in exactly the same way, whether it's running on your laptop or a remote edge OS node, or in someone else's cloud. It should all look the same. And so the way that we're doing that is developers write code in the language they want, most of the languages they want, and then we compile that code down to WebAssembly or WASM. If you don't know what WebAssembly is, you will soon. It's a new W3C standard. It was originally designed with the intent of running in your browser, and it does run in your browser. And it's another take on write once, run anywhere. The difference is that WASM code tends to be very close to machine code, and so it's very fast. And it also runs in a very secure runtime. And so it makes it such that there's a layer inside of WASM, if you will, called WASI, which in effect is kind of the system call layer for that virtual environment. And so we can have very fine-grained control over what untrusted code is doing on top of that runtime. And so in this way, customer code can run next to each other. It's very fast, it's instantaneous, it's already compiled, and it's statically linked, right? So a discrete function has everything that it needs to run. It just needs to be invoked at the time that you need it, and it needs to get to where it needs to be invoked at the time that you need it. And so we sort of take care of that magic on the net, as I'll explain in a moment. And so through this layer, we provide services like that you're accustomed to, like key value storage, which we call, again, lacking another descriptor, we call this a serverless database, which I hate. But that is essentially the idea. And so our key value storage works, as we'll talk about, on gossip and a directed acyclic graph and opportunistic dissemination. But what it means is that you, when you persist storage, like if you take a picture of Kitty here off your phone, just as a simple example, because everyone understands this, that HTTP request gets geo-routed to an edge node near them somewhere that presumably on the same network, often like 1,000 feet away or less from them at ultra low latency. So that's super fast. And then it gets persisted into our storage layer and disseminated around the network. And you can have policies on this. I want to emphasize that one of the cool things about us is that we're not just a big CDN or something. Like, you can take EdgeOS and deploy it yourself and create your own private edge nets behind your own firewall in your own facilities and so forth. That's the idea, right? And so in any case, developers write code, they push code in the network, it shows up where it needs to be, and data gets persisted anywhere and everywhere and disseminated anywhere and everywhere that it needs to be. This system is based on today's PKI. And so there's a hierarchical root of trust that looks something like this. And we have an entity model in the product, with users and groups and applications and buckets and nodes and all the things, domain names, like the things that you're largely familiar with. And that IAM model is used by each of the nodes in conjunction with PKI. It could tie into OAuth. I mean, all that's there. The way, in the beginning of an EdgeNet, there's an admin who creates a root authority somewhere. And from that root authority, he or she derives a root certificate, intermediate certificate, et cetera. And that intermediate CA is used by the EdgeOS instances. So that CA is installed, if you will, inside of EdgeOS or inside of the environment where EdgeOS is deployed. And that intermediate CA further is used by each node in its initialization process. So what will happen is that the node will generate its own public-private key pair, generate a CSR. That CSR goes back to the intermediate CA, the admin, or by policy or otherwise says approve, and then that node gets a signed certificate. And so this is what lets nodes communicate with each other, is that they do mutual certificate-based authentication. This means that it's secure. You can revoke these certificates. They can expire, et cetera. So you have this multi-layered, with all the goodness that is baked in today's PKI model. After they authenticate, they start exchanging data. And the way that data is persisted on EdgeNet is through a technique we call content addressing. Content addressing has been around a while. Other content address storage systems include like IPFS. And in fact, we share the same, we use libp2p. We're a consumer of, a piece of what came out of IPFS, but is more geared at the network layer. But we're not the same. And so IPFS is super cool, but it's a little bit slow for what we're looking to do, obviously. If you've used it, you'll know what I mean. And also, it's not designed with enterprise users or indeed anyone to have full control of their data. So like when you persist data into IPFS, it's sort of there forever as long as a node somewhere wants to have it. In our world, the data is tied to the PKI and hierarchy of trust, the whole IAM model. So you own your data, and the nodes honor the policies that you set about data, and so forth. So you can delete things. You can decide how data should be. You can decide to keep data warm, for example. You can decide to keep it cold. You can decide to keep it hot. And these are policies that you can set on your EdgeNet or that you can set in working with us. And so just in general, if you're not familiar with content addressing, if you are familiar, I apologize. This will be a bit of a digression, but if you're not familiar, the way that it works is, the kitty photo here gets submitted to a node over a protocol like HTTP. This is an EdgeOS node, and we break that down essentially into a plurality of data blocks. And each one of these blocks is signed cryptographically by your identity, again, through the same PKI, and also is hashed. So the entire body of the data block itself is hashed, and the hash is taken as the address of the block. So when you want to get kitty back, you request the hash. And so when you get the data back, you can hash the kitty yourself and verify that the thing that you asked for is actually the thing that you got in terms of the data structure. Okay. And so that stuff, all of these tiny blocks, there could be, depending on the size of the data, it could be hundreds or thousands or tens of thousands of blocks. They're stored in a hash graph like this. So each block references its parent, is hashed, so on and so forth. Just like Git, if everybody's used Git. But so Git, imagine Git plus PKI plus a network that diffuses it, and that's kind of what we are. And so, like I said, you could say we're kind of like a cousin of IPFS or something. The way that works at a low level is just, the nodes exchange routing information about blocks. And there are protocol level settings that determine how nodes behave. Some of the nodes are like really tiny. Like if you guys can see this is like a MacBook Pro server, squoze onto a credit card. So this device might have like a terabyte of NVMe, and that's it. And so you don't want this guy greedily gobbling up data blocks from the network. He is only interested in what is around, or that the users being directed to this node would be interested in. And we can run on something as small, EdgeOS can run on something as small as like a Raspberry Pi as like a gateway device, okay? And on the other hand, you may have nodes on the network that you want to persist cold data for a long period of time. In our nomenclature, we call that greedy nodes, because they look for the arrival of new data and they gobble it up and they store it forever. And so in our production EdgeNet, we have regional greedy clusters. This would be like analogous to those CDN pops, and they're always gobbling up data and ensuring that there's replication and durability for the data. So when you take this simple model of, in the first case, I submit Kitty, my New York node breaks that down into blocks, which get disseminated peer-to-peer and becomes available on other nodes. And in San Francisco, I can request the content address I got back, and the node will reassemble all the fragments and give them to me as key value blocks or as the object I requested. That's the way the system works. And so you just expand that to infinity nodes, basically. Each node can reliably keep about 125 connections open. And this connection persistence is something that helps us do a better version of CDN as well, because we can keep TCP connections open, for example, over the wide area. And even in cases where we aren't caching something, we can fetch it over a connection that's already established. And because you don't have the delay of establishing a reliable TCP connection on the window sizes ramping up and so forth, your time to first byte is a lot less. And so think about that in the context of what I said in a cityscape, or even across the world. We can bring even dynamic content that is uncacheable a lot faster to the end user. I think I mentioned this. I mean, this is the breakdown of how your developer experience works in conjunction with the EdgeNet. Basically, you write code and test it on your laptop, and the artifact that emerges from that is a compiled WebAssembly bytecode. And that bytecode is persisted, of course, as a content address set of content on EdgeNet and then disseminated. And so there are feeds and policies that state what the triggers and actions are. So basically, there's a policy that's also persisted on the net that tells a node, when an HTTP request arrives at this address, you should load and execute this function, for example. And so that's how the serverless side of this works. The next step that we're taking is to sort of move beyond just WASM and do this a little bit with unikernels that also run on WebAssembly. So these are very small, instantly bootable kernels that are, an even more secure runtime. So we're busy working on that right now. In general, you write some data into the EdgeNet like this, like you have convenience methods in your language of choice. That data gets timestamped and stored, as a hash key value. So it's stored and then retrievable basically as a blob, from the key, and the key happens to be the content address. And so reading in inverse works the same way. You request the SID. You can do the nodes do block validation, but you can also do your block validation, and then decide if you trust this data or not when you get it back from the network. Users can also have identities, so it's not just nodes or developers. We can have other users on the network who have PKI identities, and in this way, you can build a secure data integrity model across the network. And so this is saying that same thing. So with person certificates or whatever, or device certificates, you can sign the data and guarantee its authenticity and so forth. And I'm moving fast because we're running out of time. So briefly, on top of this data network, we're building other types of databases like immutable logs or immutable feeds, immutable and immutable. So immutable logs and immutable feeds. And this underneath, we resolve conflicts through a conflict-free replicated data type, a CRDT. Lots of research going on in CRDTs right now, but we're trying to make this convenient. It is effectively a last writer wins type of strategy when you have collisions in a sequence. And so you're expected to deal with those kind of things. So in other words, in the iron triangle of data persistence, like we are sacrificing consistency in favor of availability and tolerances to partitions. So that's a way of saying that all the disseminations between nodes are opportunistic. Nodes can come and go, and eventually it could be a long time, eventually things will become consistent. And so that is one constraint, or the constraint we have chosen to have at this time for working with this key value blob stuff. And feeds are just, what you'd expect. They're just, a hash graph with cryptographic signatures. So that's the high level summary. That's only 47 slides to explain it. And what I'm going to do now is just, because we're out of time, I'm just going to pull in a video, I think, if I have it. Yeah, just to give you a sense of, how we're trying to make this easy. And so I'm going to kind of run this at warp factor 5. And literally, that's too fast. So what I'm going to do first is sign up for an Edgex account. So the way this works when you've deployed your EdgeNet, or when you're in the process of deploying your EdgeNet, is you just sign up for a user account. This is what developers see. You can tie in, you can authenticate with Google, you can set up other OAuth if you want to use a different identity provider. You can do that. And we do email validation, all the things two-factor you'd expect a platform like us to do. So I'm gonna buzz through that because not particularly interesting. We've all seen people sign up for things before. Okay, so now able to log in, I'm going to get a console that shows me what I can do. And in this case, I'm a developer who has the privileges to build my own EdgeNet as well. And so you can currently see that my nodes, I don't own any nodes in the product. I haven't set up any domains in the product. I have all my my PKI, my IAM users and groups. I can set up and delegate permissions to others and so forth. So this is my little private world. And what I'm going to do is just download or log in on my node here. And then in this case, because I was doing this as like in my own environment here, I was actually doing this as a runtime. So I'm going to generate a certificate, and I'm actually going to use Docker here, I think, to download the runtime itself. And so having generated a certificate, I'm able to authenticate. I have a policy set in the backend that allows that. And so I can now, I'm going to breeze through installing the runtime, which is just a Docker pull, as you can see in this case. There's not an EdgeOS instance. And then I'm going to start the runtime. So this is like, the stuff that runs inside of EdgeOS, this is just it running in Docker because this is my developer environment. And so as soon as I do that and start up the network, you can see that the node starts discovering feeds over peer-to-peer, and it starts connecting with and peering with other nodes on the network. And so this is just some debug information that shows those messages and feeds happening in the background. And when I go back into my nodes here, I can see that I now have a node which has been discovered in Santa Clara. So basically, this is now an endpoint that can accept connections from clients. It can execute serverless functions. It can serve data as a kind of far edge CDN. And so we geolocate this. You have the option to provide the exact coordinates of where a node is, or we'll take a guess at it based on what we know about the structure of IPv4 and IPv6 routing on the internet. We'll geolocate it that way. There are other ways that we can have location hints. And at this point, I'm going to create a little demo application. So that's pretty straightforward. I think I'm going to use the CLI here. Yeah, so just pausing to take a look at the CLI. It's the kind of hierarchical command structure you're pretty used to. In our system, we have applications, which are the container for functions themselves. We have buckets, which are the container for other things like files. We have key management, organization management, user management, et cetera. Kind of what you'd expect and are probably already familiar with and working with other cloud-like tools. And so speeding up again, I'm just going to check the status of my node. It's been running 6 minutes. Here I'm checking the status of peers. So in this EdgeNet, in this private EdgeNet, I have connected to, it looks like 8 other peers. And now I'm going to create an application. So I don't know if you saw that. That's very fast. You just give it a name. So I'm going to give it the name demo app. And you can see I get this application ID, which is obviously a UUID. And so every app gets a unique identifier on the network. And I can see that it's active. So the network, the peer-to-peer net knows about it already. So already it can't accept requests, but there's nothing to do yet. And so what I'm going to do now is take this application ID and then create a function. So a piece of code that's going to run. So I'm going to do that. This version of the product, we didn't yet have our scaffolding, so I did it by hand. I'm just going to create a hello world .js, and that's going to have very simple. So there's a request and response that gets passed to the function on invocation, and then I can manipulate the request or manipulate the response objects, et cetera, directly inside of a function. In this case, in JavaScript. Although with WebAssembly, it's your target language of choice, as long as it's wasmable. Okay. I think I had to recreate the function here. So what we're going to do is give this function some memory limits. So these are like guardrails. We don't want functions to go haywire on nodes and take up too much time. So I can specify timeout limits, memory limits, and so forth. And this will control, if you're familiar with serverless and how this works in other platforms, very similar. You set up an allocation. Indeed, you are charged. Similarly, you get proportionally more CPU time the larger your memory limit is set, a la other serverless that you're likely familiar with. And so I can see now that my hello world function there is created, but it's not yet deployed. So it's ready. At this point, I'd be doing my local testing, et cetera, but I'm going to skip that and just deploy the thing. And which I think I did that here, didn't I? Oh, I think I had to rename my function. Yeah. Yeah. So I hit ASD there as opposed to actually giving the thing a real name. So I'm going to fix that very quickly. And I click save. And now I can click deploy, I believe. Oh, I'm just looking at it and changing it here and updating it, I guess. I screwed up in my demo. That's what I did. Apparently I can't type either. Okay, so I can see that I've got my function there, and I'm just going to delete it and then redeploy it because I changed that that one line of the function name itself in JavaScript. So there's my app. There's my function. How are we doing on time? I have a couple minutes, right? We'll get to the end of Hello World here.
Yes, James, we have 10 minutes. We do have some questions, but that's okay. If we don't get to them, we can make sure you're connected for sure.
Okay, warp speeding here. So I've got my function. Now it's not deployed. Now I'm going to deploy it, which I just did, deploying in the background. As I can see, it's already deployed. That means the peer-to-peer network is found it. And when I drill into this function, which I should do now, okay, in the upper right here, you'll see that application UUID there, there's a big long URI basically. And that is the application ID is effectively our namespace, and it's tied to an Edgex host name. And so when you request this gets routed to Edgex DNS servers or your DNS servers if you deploying them. These are nodes that you designate as DNS servers. And you can manage all your domains, et cetera, straight within the product. And when I try to resolve this host, you'll see that a couple of my nodes are down, they're not answering, but I get different IP addresses in order. So we can give many response strategies. You can return one host. You can return a set of hosts that are in proximity to a web client. There are reasons to do that because browsers will make efficient use of those connections, and they'll fall back to them automatically without you having to do anything. Browsers are pretty smart these days. If I trace route to the first one, you'll see that it's close to me. It's like 18 milliseconds away. If I trace route to the second one, so this is an order, of preference, right? We'll see that one is way far away. I think I had this one deployed in New York, and I think the third one here I had in India as a third node. And yet, judging by the latency, that would have been in India. So that's it. I have my little mini, 3-node CDN spanning the planet. That was too fast. That was Hello World actually running. I'll back up so you can see that. Let's go into my browser. I paste in that big long string, and I had Hello World, which is my function executing. And now I can see that I've had a number of requests. I did this a couple of times at the command line. And I have a consolidated log of those requests. So when I drill into my app and then my function, you'll see that my requests are there. We can emit, a standard request log, but I get it here in the console. I can see all my requests, and the function doesn't emit any debugging information or anything. But if it did, it would appear in the logs there as well. So I think that's pretty close. Oh, yeah. Final bit of the demo. I'm going to zip through. It works basically identically for like key value storage. So if I go in here and create a bucket, which I call demo bucket, I make this a public bucket so that anybody can read or write from it. Who's just on the web. I'm going to take a cat here and call it great cat, and then just upload it directly, as you'll see. And it's there. It also gets content addressed, as you can see on the right. And when I that was too fast. My demo ended. But as you can see, it also gets a big, long, goofy host name. And at the end of it, you can see there's a geohash appended to it. So that's the literal, gets translated to the literal node address that's closest to that particular geohash. And so that's it. That's the demo. I know I've got a few minutes left. That's it. That's everything. So questions? Hopefully this makes sense to you guys.
Thanks so much, James. We have quite a few questions, so I apologize if we don't get to your question. We will make sure you're connected to James. James, that's a great first question. What's the best way for everyone here to connect with you? Is that LinkedIn or email?
Yeah, I would just say send me an email to james@edgex.io. Would probably be best. Or you could send me a private message on Twitter too. I'm pretty responsive over those two.
Awesome. Lots of great comments on your presentation. Here is one. Would love to know more about IPFS integration in any IoT solutions for anyone working on this. And when I say IPFS, I mean any P2P tech removing the central government. Okay, that's not really a question, but.
Well, I sort of got that a little bit. So
okay.
just to be clear, we're not IPFS. We're not IPFS based. We're a cousin. We do use libp2p, which is underneath. But we have a different dissemination strategy and different services built on it, and governance and controls built in that IPFS doesn't have, even in their private cluster. So.
Awesome. Thanks for clarifying, James. Another question here. I would like to know more about how to move the code faster than a moving vehicle. That sounds super awesome. Like we will be living in the Matrix.
Yeah. Yeah. So, well, it's speed of light. So it definitely is faster than a moving vehicle. The way the dissemination happens is that the nodes understand they understand which nodes they're peered with. And so there's a split horizon there. Like there's local nodes, which are like basically a millisecond away from you or 2 milliseconds away. There's nodes that are further away, in the mid horizon, 20 milliseconds, 30 milliseconds. And then there's nodes that are like in the wide area, like, hundreds of milliseconds away across the other side of the planet from you. You can use any of those nodes to get the data that you save or to trigger a serverless function, but the nodes cooperate to make data resilient. For example, when you save something, 2 other nodes end up with a copy, but that happens in close proximity and not disseminating around the world unless that's what you want it to do. So it's pretty intelligent about proximity. And in terms of call it predictive dissemination, the idea that you want warm data to stay warm in advance of a moving vehicle, that's simply done through triggers and actions. So we can just trigger, through EdgeNet, we could send a trigger to a node that says, hey, this bucket is being used. And so you should, if you have room, you should warm it up.
Thanks, James. And are the nodes just laptops or specialized hardware?
So we run on anything pretty much that is, in quotes, a real computer. We're working with a number of different hardware vendors. We didn't talk about this, but the idea of covering the planet in computers could potentially be a very wasteful and environmentally harmful thing to do. And so we're actually taking computers, slightly used servers that are like mid of their lifespan for a normal enterprise, out of the hyperscalers. Now, these are servers that are, the hyperscalers are growing so fast, it makes sense for them to buy top of the line, state of the art stuff when they deploy. And when that stuff runs for 2 years, they purge it and buy new again because it's cheaper than building a whole new data center. And so what we're doing is we're taking the stuff they're throwing off and remanufacturing it into edge hardware. We have a partner. We announced a relationship with a company called IT Renew that does this on a global scale, and so we potentially can build this, this big planetary CDN by using existing hardware and without mining more rare earths and everything that goes with it. It's also very cost effective, as you might imagine, for us to do that. But we're also working with other vendors. Like this is a company we work with in the military space. And this, this device here is used extensively by the, by the Army, and it's coated in epoxy resin, and you can't pry off this epoxy without destroying it. So it's a very secure device. It'll run at 165 degrees Fahrenheit. It's waterproof, dustproof. I mean, we've boiled them, we've hit them with hammers, we've frozen them. I mean, they're nigh indestructible, just about. So we have a range, depending on the use case. So for the Army, it's something like this. For the pins we're putting on the streets, it could be any kind of edge computer or the refurbished equipment we talked about, or it could be stuff that you already have sitting in your data center, or IoT gateways and stuff that you already have. You can just install EdgeOS and turn on the peer-to-peer magic.
Awesome. Thanks, James. A question back from the very beginning of your presentation. When you're talking about ultra low latency, are you talking seconds, hundreds of milliseconds, or real time?
Milliseconds. I mean, we are working on, so real time is an emerging use case for us, primarily in video, because basically across industries, everyone's taking in real time video streams and doing some kind of inference to them, or taking in multiple cameras from multiple angles to try to determine exactly what the cameras are looking at in plurality. And that has to happen very fast. Obviously, in the traffic infrastructure space, where you're trying to inform a vehicle, for example, of the existence of a pedestrian in an intersection, that's ultra low latency. That's sub millisecond latency. So if you will, in the context of what's attached to an edge computing node, it's sub millisecond. In the context of multiple nodes in close proximity, it's generally less than 5 milliseconds. And in the context of like a regional area, it's 20 milliseconds. So, it depends on what's happening, but yeah, we are certainly working on all three: hot, warm, and cold in terms of latencies.
Awesome. Well, we are out of time. I apologize again if we didn't get to your question. We will make sure that you're connected directly to James. I did put his email in the chat box. We'll make sure you have his Twitter as well. And again, this was recorded so you can view the video later. Thank you so much, James. It's great to have you as part of the RITE ecosystem, and we appreciate you being with us today.
Hey, thank you everyone so much for the time and for attending. Really appreciate it.
Take care, everybody. Have a good afternoon. Bye.